Welcome to this problem walkthrough for LeetCode number 2194, titled Cells in a Range on an Excel Sheet. In this video, we'll explore how to generate all cell references between two given endpoints in Excel sheet notation. Let's dive in and uncover the solution step by step. In this problem, you are given a string S that represents a range of cells on an Excel sheet. This range is described using two cell references, separated by a colon. The first cell reference specifies the top left corner of the range, while the second cell reference specifies the bottom right corner. The goal is to generate a list of all the cells within this range, sorted in lexicographical order. When we talk about lexicographical order, it means that column letters are compared first, so column A comes before column B, and so on. Within the same column, rows are compared numerically, meaning row 1 comes before row 2. The input format for the problem is a single string, such as A1Z9, where A1 is the top left cell and Z9 is the bottom right cell. The output should be a list of strings representing all the cells in this range, ordered lexicographically. Let's take a look at the first example. Here, the input string is S equals K1 L2. The range begins at cell K1 and ends at cell L2. This means the columns involved are K and L, and the rows involved are 1 and 2. To determine the output, we need to generate all combinations of these columns and rows, starting with column K and listing its rows 1 and 2, followed by the rows for column L. When we organize these cells lexicographically, the result is the list, K1, K2, L1, L2. This illustrates how the range is expanded and ordered. Now, consider the second example, where the input is S equals A1 F1. Here, the range begins at cell A1 and ends at cell F1. This time, the columns involved are A, B, C, D, E, F, but the row involved is only 1. Since the range spans a single row, we simply list all the columns in their natural order from A to F, while keeping the row number fixed as 1. The resulting output is A1, B1, C1, D1, E1, F1. This example highlights how the problem handles ranges that stretch across multiple columns but remain within one row. Next, in example 3, the input string is S equals C3 E5. The range starts at cell C3 and ends at cell E5. This means the columns involved are C, D, and E, while the rows are 3, 4, and 5. To generate the output, we list all cells column by column. For column C, we include rows 3, 4, and 5, resulting in C3, C4, and C5. Then, for column D, we again include rows 3, 4, and 5, and finally, for column E, we do the same. When we arrange these cells in lexicographical order, the final output is C3, C4, C5, D3, D4, D5, E3, E4, E5. This example demonstrates how the solution handles ranges that span multiple columns and rows. Finally, let's review the constraints and edge cases. The input string S will always be valid and follow the format A1Z9. The length of the string S will be between 1 and 8 characters. The column letters are uppercase English letters from A to Z, and the row numbers are positive integers. Additionally, the starting cell reference is always guaranteed to be lexicographically smaller than or equal to the ending cell reference. The range will not extend beyond 26 columns or 9 rows. Some key edge cases to keep in mind include, if the range contains only a single cell, such as C3 is C3, the output should be C3. If the range spans one row but multiple columns, for example, A1 is Z1, the output should include all columns in that row. Similarly, if the range spans one column but multiple rows, such as A1 A9, the output should include all rows in that column. Finally, if the range reaches the maximum limits, such as A1 Z9, the solution must generate all cells in lexicographical order. To solve the problem cells in a range on an Excel sheet, we need to extract all cell references from a given range specified in a string like A1C3. Here, A1 represents the top left corner of the range, and C3 represents the bottom right corner. Our goal is to generate a list of all cell references within this range in lexicographical order. One approach we considered is the brute force method, where we iterate through all rows and columns within the specified range. For example, given the range A1C3, we loop through the columns A, B, C in rows 1, 2, 3, combining the column and row indices to create each cell reference. This is done using two nested loops, one for the columns and the other for the rows, thereby constructing all possible cell names within the range. The brute force approach has its merits. It's straightforward and directly aligns with the problem's requirements, making it easy to implement. In terms of complexity, the time complexity is O, n asterisk m, where n is the number of rows and m is the number of columns in the range. The space complexity is also O, n asterisk m, to store the resulting list of cell references. However, this approach doesn't introduce any additional insights or optimizations. To address this, we explored an optimized approach that utilizes the ASCII values of the column letters. Since Excel columns like F, B, C correspond to ASCII values such as 65, 66, 67, we can iterate directly over these character codes. This eliminates the need for manipulating strings, resulting in a cleaner and more efficient implementation. Another alternative we considered was mapping column letters to numerical indices, such as A equals 1, B equals 2, and then converting them back to letters when generating the output. However, this method adds unnecessary complexity without any real performance benefit. After evaluating the options, we chose the optimized approach for its simplicity and efficiency. The key insight was recognizing that column letters align with their ASCII values, allowing us to iterate directly using character codes. This avoids redundant operations, such as converting between letters and numbers or performing string manipulations, making the implementation more streamlined. While the brute force and ASCII-based approaches have similar performance in terms of time complexity, the ASCII-based solution stands out for its clarity and reduced overhead. Mapping columns to numbers was ultimately discarded because it introduces additional steps without offering any tangible improvement. This makes the ASCII-based optimized approach the most practical and elegant solution for this problem. When comparing the complexity of the approaches, both the brute force and optimized methods share the same time complexity of O, n asterisk m, where n is the number of rows and m is the number of columns, as well as a space complexity of O, n asterisk m, for the result. However, mapping columns to numbers introduces an additional O, n, overhead for the conversion, which makes it less efficient overall. In conclusion, the optimized approach strikes the right balance between simplicity, clarity, and performance. By leveraging the direct relationship between column letters and their ASCII values, we achieve an intuitive and effective solution that meets the problem's requirements with minimal overhead. In this problem, the input is a string that represents a rectangular range of cells on an Excel sheet, formatted like A1-C3. This format specifies a range that starts from the top left cell, here A1, and extends to the bottom right cell, which is C3. Our goal is to generate all the cell references within this range in lexicographical order. Lexicographical order means we process the columns first, moving from left to right, and within each column, we process the rows from top to bottom. To solve this, the first step is to parse the input. From the string, we extract the starting column and row from the first part, e.g., from A1, we get A as the starting column and 1 as the starting row. Similarly, we extract the ending column and row from the second part, e.g., from C3, we get C as the ending column and 3 as the ending row. Next, we generate the columns for the range. By using the ASCII values of the column letters, we can calculate the range programmatically. For example, the ASCII value of A is obtained using the ORD function, and we can iterate from ORD A to ORD C plus 1 to generate the sequence of columns A, B, and C. This method makes it efficient to handle column ranges of any size. Now that we have the column range, the next step is to generate the rows. The row numbers are already represented as integers in the input, so we can directly use Python's range function to iterate through the rows. For instance, if the rows span from 1 to 3, we can generate this range with range 1, 4, which gives us 1, 2, and 3. After generating both the columns and the rows, we need to combine them. For each column in the column range, we iterate through all the rows and concatenate the column letter with the row number to create the cell reference. For example, for column 1 in rows 1, 2, and 3, we generate A1, A2, and A3. This process is repeated for all columns in the range. Finally, we store all these cell references in a list and return it as the output. The way we process columns first and then rows ensures that the output is naturally in lexicographical order without requiring additional sorting. There are a few important insights about the solution. First, the lexicographical order is achieved by iterating through columns first, from left to right, and then through rows, from top to bottom, ensuring the result meets the problem's requirements. Second, the use of ASCII calculations with the ORD and CHR functions allows us to handle column ranges efficiently, even when the range spans multiple letters. For example, this approach works seamlessly for ranges like A to Z. Third, instead of pre-computing a large grid of all possible cell references, we dynamically generate the references by combining column and row ranges. This makes the algorithm more memory efficient. The data structures used are straightforward: strings to parse the input and a list to store the output. This simplicity ensures the solution is easy to implement and understand. Let's walk through an example to see the algorithm in action. Suppose the input is A1 C2. First, we parse the input to determine the start and end points. Here, the starting column is A, the starting row is 1, the ending column is C, and the ending row is 2. Next, we generate the column range, which gives us A, B, C, by iterating from ORD A to ORD C plus 1. For the rows, we generate 1, 2 using range 1, 3. Now, we combine the columns and rows. For column A, we combine it with rows 1 and 2, generating A1 and A2. Similarly, for column B, we get B1 and B2, and for column C, we get C1 and C2. Combining all these results, the final output is A1, A2, B1, B2, C1, C2. Regarding complexity, the time complexity is O, M*n, where M is the number of columns and N is the number of rows, as we generate one cell reference for each column-row pair. The space complexity is also O, M*n, to store the output list. Some edge cases to consider include single-cell ranges like A1 A1, which should return A1, and large ranges like A1 Z1000, where the algorithm must handle a high number of cells efficiently. Finally, it's important to validate that the input always adheres to the correct format to avoid errors. The solution begins by defining the cells in range method, which takes a string S as input. The string specifies a rectangular range of cells in Excel format, such as A1C3. First, the input string is parsed to extract the starting column, start_call, starting row, start_row, ending column, end_call, and ending row, end_row. These components are derived from specific indices in the input string, S0 for the starting column, S1 for the starting row, S3 for the ending column, and S4 for the ending row. Next, an empty list named result is initialized to store the cell references. The solution proceeds with two nested loops to generate the cell references. The outer loop iterates through the columns in the range, using the ORD function to convert the column letters into their ASCII values. This allows iterating through the character range from start_call to end_call. The CHR function is used later to convert the ASCII values back into letters. The inner loop iterates through the rows in the range, converting the start_row and end_row strings to integers using the int function. For each combination of column and row, the cell reference is created by concatenating the column letter from CHR, call, and the row number as a string. This reference is appended to the result list. Finally, after all iterations are complete, the result list contains all the cell references in lexicographical order, and it is returned as the output. The solution ensures correctness by iterating in row major order, columns first, then rows. This implementation is efficient, as it directly constructs the cell references using straightforward loops without additional sorting steps. The time complexity is proportional to the number of cells in the range, making it well suited for the problem's constraints. This is the Java implementation of the cells in a range on an Excel sheet problem. The approach mirrors the Python solution, converting the range string into start and end components for rows and columns, and iterating through these ranges to generate the cell names. Key differences include Java's type declarations, use of the ArrayList class for storing results, and handling characters and strings with Java's char and string types. In this example, the input string is S equals A1 to B2. The first step is to parse the input string into its components. Here, start_call is extracted as a start_row as 1, end_call as B, and end_row as 2. This breakdown allows us to clearly identify the starting and ending columns and rows of the range. Next, we initialize an empty list called result to store the final output. Now, since columns are represented as characters, we convert them to their corresponding ASCII values. For A, the ASCII value is 65, and for B, it's 66. This defines the range of columns we need to iterate over, which is from 65 to 66, inclusive. With these steps completed, we are ready to start iterating through the columns and rows to generate the cell values. We begin with column A, which corresponds to the ASCII value 65. For this column, we iterate through its rows. The first row is 1, so we append the cell A1 to the result list, making it A1. The next row is 2, so we append A2, updating the result to A1, A2. Moving to column B, which corresponds to the ASCII value 66, we repeat the same process. For row 1, we append B1, resulting in 1, A2, B1. For row 2, we append B2, and the final result becomes 1, A2, B1, B2. At the end of these iterations, we return the result list, which contains all the cells in the specified range. In the second example, the input string is S equals C3 D4. First, we parse the string to extract the components. Here, start_call is C, start_o is 3, end_call is D, and end_o is 4. With these components identified, we initialize an empty list called result to store the output. Next, we translate the column letters to their ASCII values. The ASCII value of C is 67, and for D, it's 68. This means we will iterate over columns from 67 to 68, inclusive. This setup ensures that we can systematically generate all the cell values within the specified range of columns and rows. Starting with column C, which has an ASCII value of 67, we iterate through its rows. The first row is 3, so we append the cell C3 to the result list, making it C3. The next row is 4, so we append C4, updating the result to C3, C4. Next, we move to column D, which corresponds to the ASCII value 68. For row 3, we append D3, resulting in C3, C4, D3. For row 4, we append D4, and the final result becomes C3, C4, D3, D4. Once all iterations are complete, we return the result list, which contains all the cells in this range. In the third example, the input string is S equals E5, E5. Parsing the string, we find that start_call is E, start_o is 5, end_call is also E, and end_o is also 5. This means the range consists of just one cell. As before, we initialize an empty list called result to store the output. Converting the column letter E to its ASCII value, we find that both the start and end columns are 69. Since the range includes only one column and one row, our iteration will be very straightforward. For column E, which corresponds to the ASCII value 69, we iterate through its rows. The only row is 5, so we append the cell E5 to the result list. This makes the result list E5. Since there are no other rows or columns in this range, the iteration is complete. We then return the result, which is E5. This demonstrates how the solution handles a single cell range effectively and efficiently. In this function, cells in range, the time complexity is determined by analyzing each step of the process. First, extracting the components of the input string, such as start_call, start_o, end_call, and end_o, involves simple slicing and indexing. Since the input string is always fixed at 5 characters, this operation takes constant time, or O1. Next, we consider the outer loop that iterates over the columns in the range. This loop runs 4 C iterations, where C is the difference between the ASCII values of end_call and start_call, plus 1. Inside the column loop, there's an inner loop that iterates through the rows. This loop runs 4 R iterations, where R is determined from the difference between end_o and start_o, plus 1. Each iteration of the inner loop involves creating a string for the current cell and appending it to the result list, both of which are constant time operations. Together, these steps lay the foundation for the overall time complexity. Now, combining the iterations across both loops, the total number of iterations is the product of C and R, representing the number of columns and rows in the range. As a result, the overall time complexity is O, C*R. Shifting to space complexity, we account for the memory usage of both the result list and any temporary variables. The result list contains one string for each cell in the range, and since there are C**r cells, the space required for this list is O C**r. Additionally, the temporary variables used during the computation, such as the column and row indices, require a constant amount of space. Since these variables do not scale with the size of the input, their contribution to space complexity is O(1). When combined, the dominant factor is the result list, leading to an overall space complexity of O C**r. Looking at a comparison, a naive approach might involve generating all possible Excel cells upfront, such as from A1 to Z99, and then filtering those based on the given range. This brute force method would result in significantly higher time and space complexity, as it would involve creating and filtering a much larger dataset. In contrast, the optimized approach here efficiently narrows its focus to the specified range, iterating only through the relevant columns and rows. This ensures that both time and space complexity are proportional to the size of the range, or O C**r. When analyzing best, average, and worst-case scenarios, the best case occurs when the range contains only one cell, like A1, where both C and R are 1, resulting in O(1) complexity. For average and worst-case scenarios, the complexity grows linearly with the range size, as the algorithm's performance is directly tied to the number of cells it processes. Finally, let's justify the big O notation mathematically. With nested loops, the outer loop iterates over C columns, and for each column, the inner loop iterates over R rows. This results in a total of C**r iterations. Within each iteration, the operations performed, string concatenation and appending to the result list, are constant time operations. Since there are no additional layers of complexity beyond these loops, the time complexity is directly proportional to the product of C and R, resulting in O C**r. Similarly, the space complexity is dominated by the result list, which stores one string for each cell in the range. As the number of cells is also C**r, the space complexity is O C**r as well. This systematic breakdown confirms both the time and space complexities of this algorithm. When solving this problem, there are several common mistakes to avoid. First, be cautious with loop ranges. A frequent issue is using the ASCII value of the bottom right column, like C, as an exclusive upper bound. Remember, ASCII values are inclusive, so failing to account for this can leave out the last column in your range. Next, mixing up rows and columns in nested loops can lead to incorrect cell ordering. For example, if you iterate over rows inside the column loop, the output won't follow the expected left to right, top to bottom sequence. Another mistake is hard-coding the bounds for columns and rows, assuming limits like AZ or 1 to 100. Excel supports far larger ranges, such as columns up to XFD and rows up to 1,000,000, so your code needs to be flexible enough to handle these cases. Now, let's discuss a couple more pitfalls to watch out for. Inefficient string manipulation is a big one. For instance, concatenating strings in a loop, such as using result plus equals new underscore cell, can slow down your code significantly. This is because string concatenation in Python has O(n) complexity, and doing it repeatedly in a loop leads to O(n²) performance for large ranges. A better approach is to append to a list and join the strings at the end, which operates in O(n). Another common oversight involves ignoring edge cases. For example, ranges like A1 or C1 and D1 represent scenarios where either the rows or columns are constant. If your loops aren't carefully configured, these cases might produce off-by-one errors or even empty outputs. Always validate your code against these edge cases to ensure correctness. Understanding this problem also provides valuable insights for interviews. One key takeaway is recognizing the pattern of iterating over Cartesian products, such as rows paired with columns. This is a foundational concept that appears in many grid-based problems, like matrix traversal. Additionally, handling edge cases gracefully, such as clarifying the maximum range size or accounting for invalid input formats, highlights your attention to detail. Optimization is another critical aspect. While an O(n²) solution is acceptable, writing clean and efficient code demonstrates your ability to handle large ranges effectively. Finally, be prepared for follow-up questions. For example, you could be asked to handle more complex scenarios, such as ranges that include merged cells or non-contiguous areas like A1C3, E1E3. Thinking through these variations will help you stand out. This problem also links to several related LeetCode problems that can deepen your understanding of grid traversal. For instance, in LeetCode 54, Spiral Matrix, you'll encounter similar traversal concepts but with a specific spiral order requirement. LeetCode 73, Set Matrix Zeros, also deals with rows and columns, but the focus there is on efficient in-place updates. LeetCode 200, Number of Islands, explores traversal across grids in the context of graph traversal techniques. Finally, LeetCode 566, Reshape the Matrix, challenges you to manipulate grids, which is excellent practice for handling boundary conditions and transforming matrices. These problems collectively reinforce the importance of mastering Cartesian products and grid-based logic. Now, let's compare a few alternative approaches and their trade-offs. The brute force method involves using nested loops to iterate over rows and columns. It's simple and intuitive but may become slow when working with very large ranges. Alternatively, you could use Python's itertools.product to pre-compute the Cartesian product of rows and columns. This approach is concise and elegant, leveraging Python's libraries for efficiency, but it assumes familiarity with those tools. Another optimization involves handling string manipulation. Instead of concatenating strings in a loop, you can use list-based operations and join the strings at the end. This method is faster for large ranges but may require extra steps to manage the intermediate list. Each approach has its pros and cons, so choose based on the problem constraints and your goals for clarity and efficiency. Great job working through this problem. To summarize, we used ASCII values and nested loops to generate a list of cells within the specified range. Remember, this approach is efficient for small to medium ranges and highlights the importance of working with string manipulation in coding. Thank you for watching, and don't forget to like and subscribe for more content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!